What we're looking at here is a picture of plasma on the atmospheres and outer layers of the sun, swirling around, doing these crazy motions due to the solar magnetic field. The sun is producing this incredibly intense, strong magnetic field due to the amount of ion materials, hydrogen stripped free of electrons, swirling around rapidly. And these plasma materials, that's the source of the solar wind. These charged particles. Remember, plasma is a charged gas. So some of these can be flung off and just shot out through the solar system. And that's the origin of this solar wind. In other regions of the sun, those strong magnetic field lines are going to pinch material, squeeze it together, give it a specific preferred direction of flow. And that's what produces sunspots. Now, the naming scheme, the conventions here, comes from the concepts of shadows. That's not to imply that these are shadows. This umbra is still an incredibly hot region of the sun. Recall, this is in the photosphere layer. So this here, the granules here, are around, rounding, we'll call it 6,000 Kelvin, whereas this is a little bit cooler, somewhere between 100 to maybe 1,000 Kelvin degrees. Not degrees, that's degrees Celsius. About 100 to 1,000 degrees Celsius cooler than the surrounding granules in the photosphere layer. So why the naming of shadow conventions umbra and penumbra? That just goes back to how you see the sunspots. You never look directly at the sun. What you do is you set up systems to cast the light into a box that you can safely peer at. And so that's the origin of the shadow name. So going through this, umbra, that's going to be the dark, cooler region of the sunspot. Penumbras is going to be the region around this where the material is flowing in. Remember, this is being produced by magnetic field lines. Whereas the granules is just bubbling seas of plasma floating around on the surface of the sun. Now call back to material we've covered before about probing the nature of the sun. We talked about how we could do helioseismology, measure the sound waves bouncing in and out of the sun. Well, that helps us visualize the interiors of these sunspots. And we see the magnetic field lines as they have these crazy patterns, bringing material down, oozing outwards, spinning around. And these sunspots are not fixed to the sun. They will actually rotate around the sun. Here's a picture of one starting on March 26th, going for a couple of days into April as the sunspot literally rotated across the surface of the sun. So the sunspots move. That's to say that the magnetic field lines that's creating those sunspots can also move across the surface of the sun. Now the frequency of sunspots we see in the sun, it follows what we call this 11-year sunspot cycle. Now I'm sorry, this is going to be a little bit confusing, so I'm going to say this twice just to try and clarify this. This sunspot cycle, this 11-year, is actually part of a full 22-year-long cycle. What's happening basically is the magnetic field of the sun. All right, here's our sun, magnetic field, north, south. All right, every 11 years, that field will switch, where now this is north, this is south. So this is 11 years, and then wait 11 more years, north, south. So a total of 22 years have passed by. So what's happening is that the magnetic field of the sun is constantly switching, right? About every 11 years, north to south, then south to north, and back. So the full cycle is 22 years to go from north, down, back up. But we focus on the sunspot cycle because during these transitions, when we're in the flipping, that's going to talk about when we see a maximum number of sunspot cycles. So For now on, we'll focus on, say, the 11-year sunspot cycle, meaning that every 11 years, the number of sunspots that we see increase. Tracking the sunspot cycle is very important for us because when there is a lot of activity, there's going to be an increase in the solar wind. Ever heard of power outages, blackouts caused by solar storms? Yeah, this correlates to the sunspot cycle. When there's an uptick, when you see a lot of sunspots, the sun is very active. Magnetic field lines are moving around rapidly, changing, throwing lots of material. So we want to track the number of sunspots and know the solar activity. The sun has this natural rhythm. One point of interest, though, as we've been counting the number of sunspots for literally centuries, there was a dip known as the Maunder minimum, where the number of sunspots we observed just diminished for some reason. We're still speculating what caused that and what that is. To explain the solar cycle, we're going to use what's called the magnetic dynamo theory. And this is a process to try and describe how the magnetic field lines get all twisted, kinked, and flipped around. Basic principle here is, imagine you have magnetic field lines going through the center of the sun. And you could picture this as a bar magnet of the North Pole and a clearly defined South Pole. But the material making this magnetic field is rotating. So as it rotates, it starts to bend the magnetic field, starts to twist it with it. And if it rotates fast enough, you're going to start getting these weird kinks and this strange behavior in the magnetic fields. Here, let's cut to a little video showing this magnetic dynamo theory in action. Go ahead and start the animation and watch the lines start to swirl around, twisting. Magnetic field lines is getting all kinked up. Here's the swirling again at the beginning. The magnetic field lines start to extend out and then loop, twist around, and that creates the crazy complex patterns. Think back to the plasma field lines we saw at the beginning of this video, the constant arcs and swirling. Well, here's your arc and swirling created by the magnetic field lines looping around the sun. Finally, here's some footage of this solar activity in action, seeing how the plasma is arcing around, pinching back down into the sun. This is what we mean by about solar activity, and this is what's going to lead us to our discussion about the solar storms on the sun. During this uptick in activity, you can have examples of material in the sun being flung out there. These are what we call solar prominences, just hot rising gas in the chromosphere. It's trying to be constrained by the magnetic fields. So, when there's enough activity, especially during these uptick in solar spots, you'll have solar flares and resulting coronal mass ejections, meaning that material on the upper layers of the sun are just being flung out, thrown out into the cosmos. These things will have a lot of energy, and they're going to be very violent. The activity, the number of solar flares, here's in coronal mass ejections, correlates to the sunspot activity. When the magnetic field is doing all these crazy kinks and bends, the amount of activity on the surface is upticking, and the magnetic field lines can suddenly snap, and that snapping of field lines is what erupts the material outwards. And when that happens, we'll have these solar storms that are powerful enough that they can literally disrupt power grids, shut down satellites in space. And of course, they'll cause these brilliant auroras here on Earth. Recall, an aurora is charged matter just interacting with our atmosphere. Now, the reach of the sun's magnetic field, while crazy and complex on its surface, extends all the way out to about 100 astronomical units away from the sun. Remember this plot? We've seen this before. We have Earth at 1 AU, and the heliopause, or the heliosphere. This is the outer limits of the sun's magnetic field strength, and this gives you an idea of just how massive, how powerful the sun is, and how far away its magnetic field stretches out. So it's very important to us that we are constantly monitoring the sun, keeping a track of its activities. In fact, we actually monitor the sun 24/7, and we use that to predict like weather forecasts. Here are two websites that you can go to track the information out there, see what the weather reports are in terms of the sun's activity. So to start recapping things, what's the life cycle of our sun? Well, we can talk about the life cycles of stars in general. And you have the massive stars, or star like our sun, which will be the medium, the middle-sized stars. And they started off from that big nebula that we keep talking about, that nebulous hypothesis. Gas, mostly hydrogen, compressed down, formed a protostar, and that protostar eventually built up enough mass to start fusing in its core, turning into our sun. Now, in the later, a couple billion years from now, the amount of hydrogen burning in the sun is going to start running out. And when that happens, the sun is actually going to swell up in size and turn into what's called a red giant. Eventually, even as a red giant, that star will, our sun, run out of material to fuse. And at that stage, because of how massive our sun is, it's going to just start eking its material away. This is what we call a planetary nebula. It starts just spitting out its outer layers, throwing it off itself, and what we'll leave behind is this hot white dwarf, basically the remains of the core of the sun. This isn't fusing, but this thing will glow bright for millions of years as it slowly radiates all of its hot energy away. Whereas the material that the sun has spit out, thrown away, well, that'll create into a new nebula and form the next generation of stars. To recap section 13, we've probed the sun's interior by measuring the neutrinos produced in the fusion processes and used helioseismology to track the density, the depth of material. This fusion is a result of understanding our fundamental forces. Recall we set up there are four: gravity, electromagnetism, the nuclear strong, and the nuclear weak force. Holds planets together, holds molecules together, holds nuclei together, breaks the nuclei. And so the sun is generating tons and tons of energy through what's called the proton-proton chain. That's how you fuse 4 hydrogen atoms into 1 helium atom, and all the energy that we get to gobble up and consume. And to wrap things off, we talked about the sunspot cycle, which is this 11-year solar cycle. And results in upticks in solar activity. The number of sunspots goes up during these solar cycles at maximum activity. So with that, we'll call it in section 13, and we'll see you all next time.